Yes, welcome to lecture number 10 in parallel and distributed computing. So now we come to a topic that has gained kind of a little bit attraction due to artificial intelligence, but maybe also not, because artificial intelligence uses a lot of GPUs, in particular GPUs from NVIDIA, apparently. And GPUs from NVIDIA are programmed usually in a programming language called Cuda. However, artificial intelligence uses some tools already like PyTorch and something like this. PyTorch, what's the name of the other one? TensorFlow, right. So actually this is something we are not talking about, because we are not talking about the tensor and these tensor operations that have been introduced kind of a little bit more recently, you could say, in particular to do fast matrix multiplications, which is required for doing artificial intelligence. So there is also something that's called okay, so I've forgotten the name again. Okay, so there are special units for executing neural networks, even for smaller processors, like they have neural cores or something like this, neural network cores or so. What they basically do is they have units to do this fast matrix vector multiplication. It's an interesting topic, but here we don't cover everything, we cover only the basics, and we go on talking about the basic of Cuda. Yeah? So I actually hate to talk, nowadays I have to do this a lot, on things that are run by specific companies. Yeah? So here, this is Cuda is just for NVIDIA graphics cards. So they did a pretty good job in providing a good interface to do general computation, yeah, which other competitors apparently did not. And so this gave NVIDIA, in my interpretation, an edge in so to speak, a software edge, yeah, in being the provider of graphics cards. So they got a lot of, so you know how this works. They got a lot of money. They built, then they could invest, and so they are now the absolute market leader. Yes, so there is, of course, other companies, in particular, ATI, right? That also provides fast graphics cards, and what they did after many years is, okay, we also need something similar to Cuda, and they basically cloned Cuda and called it HIT. Yeah? So we are not, good morning, we are not now talking about HIT here, but HIT is almost identical in everything to Cuda, because it's kind of a clone of this, but it can also run on a few other graphics cards that are not by NVIDIA. Okay, so, right, having said this, let's get started. So yes, we have we talk a little bit about the basics here, what we have to do with allocating memory, understanding global and device functions, and how all of these things actually work. So now first things first. So this is how my colleagues, I have to admit, somebody prepared these slides for me because I inherited this lecture. Yeah. So okay, this is what I kind of want to say. So we in this institute we are using Cuda since version 1, since I believe 27 or so. Yeah, and my predecessor actually now works for NVIDIA. Yeah, as in Houston. So, but he knows a lot more about these things than me. I actually only inherit these things. Talking about the difference between a CPU and a GPU. Yeah, so the idea in a CPU is you have a pretty strong processor. It can do a lot of things, and nowadays you will have you'll have multi-core processors. Yeah, that also have their own cache. Yeah, shared cache and their own cache, and they have a pretty big core usually, because processors can do a lot of different tasks. And also there are historical reasons, and also you can also always think, why is Apple always faster? Why is Apple always fast? So, okay, I'm again bashing some companies. Apple can be fast because Apple does not do what others call backward compatibility. Yeah, so you have to some Apple users here. Yeah, so you have to after 3 years you have to throw away you throw away your computer, but they also throw out concepts. So you cannot run the old software easily on a new computer because they don't use backward compatibility. They always want to be at the edge. So there's the other concept of we need to have backward compatibility. That means that, for example, these x86 architecture, they always add up new stuff. Yeah, so they go through this evolution, like when a human gets born, so they go through all the steps that they had in between, if you will. And this is in a sense with these processors, they still carry all the weight of what they had in the 70s. Yeah, is still all in these processors. So they get fatter and fatter and fatter. And if you remove some of these things and make things from scratch, then it may be more streamlined and actually faster than what we have here, but then you have the problem of no backward compatibility. So anyway, on a CPU we have these large processors with a lot of control function, and actually the most size here is in the cache. So these things can only do a few things at the same time. Whatever they can do at the same time can also be completely independent of each other, unless you're using AVX, for example, right? So this is the place where you do vector optimization, where you use SIMD even on a CPU. Now, in comparison to this, a graphics card is there to. So graphics cards, of course, is invented to process pixels on the screen. And so usually there are many pixels, and the operations that you do on the pixels are in generally most of the time all the same. So you want to display, you know, a picture. So, or you want to, what should I say? You want to make this, change the color saturation of a picture somewhere. So then, of course, you have different pixels, so different data, but you always do the same operation. So for this, it is more useful to have many processing units at the same time, but they in generally do the same things. Or most of them do the same things. So this means you are better off with a SIMD, single instruction multiple data. You have a very simple control structure, but you have many cores that do the same thing at the same time. Also, here you have not that much cache. Nowadays they have more cache. They started off with no cache at all. Or they have a better, okay, so they used to have kind of a programmable cache. That's called shared memory. Is another topic we'll not touch today in this one lecture that we have on Cuda, yeah. But you could think about this, so you have some control on the cache, where on a CPU usually the cache is something that's invisible to you. Now NVIDIA kind of discovered, if you will, that this can be useful for scientific computing in another way. And so they got a little bit popular with some other things. And historically speaking, I don't know how much time I'm now wasting, but since I'm so old, I can remember all these things that came along. So you should know that what we are doing here, scientific computing, is from a market, from an economical point of view, irrelevant. Yeah? So you should not research, right, if you do research in how you can save memory from energy, for example, solving partial differential equations, you are not doing useful work. You should try to reduce energy consumption for watching YouTube videos, because this is where I mean, okay, nowadays you should, okay, so this is, again, I'm old-fashioned. Nowadays you should try to reduce energy consumption from ChatGPT. So this is the most dangerous thing in the moment, yeah? Now, the problem being, before there was artificial intelligence, or before artificial intelligence came so widespread, I mean, artificial intelligence was there 20 years ago too. The scientific research community was not really a market. Meaning that when hardware, and there was some hardware like cell processor also, when hardware was produced dedicated for scientific research, then some research lab bought one or two of these devices, and then the company got bankrupt, yeah, or just didn't follow up to this, yeah. So I think in the first lecture, don't you remember this? There's the Moore law, the first Moore law and the second Moore law, and everybody just talks about the first Moore's law. The second Moore's law is that the cost of a factory to build these devices grows exponentially the same way as the cost for one device decays exponentially. So there are very, very few players in the world who can actually build cutting-edge semiconductor technology. There is many, many companies that can build, devices for dishwashers, yeah, and they are. Processors for dishwashers are pretty strong compared to what I was growing up with as a computer, yeah. But what is cutting edge is different. So now, what changed here is that these GPUs were built for players, and they are a market. Yeah? So there was an economic incentive to actually build these devices. And we, as researchers, we could now buy these devices to do our research with this. And now again, me old guy, yeah. What NVIDIA also did is they built some of these devices for consumers, and the processor was the same. They did not change a lot to this, but they made some adjustments. So, for example, they would offer the memory of the GPU for the GPU, say. So the memory is not on the GPU. It's not on the die. Yeah, it's all around it. And if you look in how they are built, they put the dies of the memory just really physically next to it, but it's not on the same die. So you could for some time now buy a GPU with actually protected memory. So what you have to know about, so that you can actually do real computation with this. Okay, telling you the story how research works with GPUs back in the day, because I'm doing this now for really decades now. So 15 years ago, what you would do is you would buy a consumer card, because you'll try to take consumer cards because they are much cheaper than cards with protected memory, which also existed back then. Then you basically you buy 2 or 3 of them, you test them, and you take the one that works. Yeah, and the other one goes in the computer of the secretary or something, or you use it just for displaying your graphics. Yeah, so these I would say the memory of a usual consumer graphics card is a Geiger counter. Yeah, it gives you random output. Yeah, it's not protected, so it can generate anything. And sometimes these things are good, and sometimes they are bad. Yeah, so you cannot tell them so that the memory is broken, because they are absolutely fine. Yeah, if you sometimes get 1 pixel wrong, yeah, because the memory doesn't work properly, you don't notice as a human. Yeah, but in your computation you notice. So then we have good cards and bad cards, and sometimes when you lose them for a long time, then they become bad cards, and then they go to the storage, yeah, or is used by somebody. So this is why we in our office we all have this very professional gamer cards for all of this time. Okay. Sorry for telling you I should actually go on with what we are here actually doing. So yes, SIMD on the GPU. And the GPU is specialized for high parallel computations, because it was used the idea is to use it, the original idea was to use it for graphics. Then, I mean, actually NVIDIA was so clever to get into research things, and then they got into the artificial intelligence market, and then this again is something that, of course, takes, which is really a market now, yeah? So in this context, we talk about threads in a little bit a different, with a little bit a different meaning from what we have in threads. For example, it is the P threads in C++. So P threads the usual threads in C++, they run independently on different cores, while a thread in the on the GPU is just one thread of execution, but which is done in a SIMD version of. So all the threads that run in parallel, yeah, they executing the same code. So they are organized on a grid, which I believe has some historical reasons coming from a graphics processing perspective. And they are not, you could think about them all being executed in parallel. In reality, they are of course not all executed in parallel, but there are many core. I think there was, okay, so this is already some time ago, but I'm not keeping up to date. So what we have, for example, in our Phoenix, we have NVIDIA Tesla P100, and they have 3,584 cores. You see, this is 9 years old, yeah? So the H100, for example, has 16,000, 17,000. And exponential growth, I think it's whatever I write here, it's tomorrow, it's no longer important. So they can execute many of them, things in parallel. So what I say here, each thread processes one entry, is so of course also in Cuda you can write the same kind of program that you would write in usual C++. So you know you have a matrix and you go through. You have a loop over the different entries. This is a possibility that you can do in Cuda too. But usually what you would do is you would use every entry that you would otherwise have in a loop with its own thread. Yeah? And what is, so you have a different approach to programming. What also helps here is that Cuda has something that's called the, I think it's called zero overhead context switch. Heard about this? So, so what is context switch? If you think about the CPU, and you think about multi-threading. So usually your computer has something of the order of 4 to 20, 24 cores, and they are running thousands of threads at the same time. Yeah. So then obviously these threads are not executed in parallel but sequentially, and they go from one thread to the other thread. So what do they need to do when they go from one thread to the other thread? Because every thread has what we call a context. The context is its memory. Basically, it's it's the memory that it has on the heap, yeah? Also the memory that it has on the stack, but these are things that are kind of outside, yeah? So usually that's not a problem. You just leave them alone and you go to another stack. What really matters is that in a context, you have your registers loaded. Yeah, so you're doing something, so you have these in your registers, and now you are switching the context. So what you need to do, what the processor has to do, is to take everything that it has in the registers and puts it to the stack that belongs to that particular thread. And then it goes to the other threads where that it previously executed already. It loads everything, all the registers from their stack, goes on for a few cycles, then it puts all its registers again on that stack and takes things again from the other stack. So this is context switch. And you see that context switch is expensive because you always have to save your registers. And in Cuda, this works a little bit differently. So these processors have a lot of registers. And instead of saving the registers on a stack, they switch to other registers. So they never move the memory around, so they just turn to other registers, and this does not, so this goes in a single cycle. So they don't, so this is what they call no overhead. So in Cuda, supposedly it does not cost anything to go to another thread. Yeah? Whereas on a CPU, if you programmed on a CPU like you do this in Cuda by executing each entry in your matrix by its own thread, this would be very costly because every time it has to switch the context. Okay. Having said this, so right. A little bit of nomenclature. So we distinguish between the machine in which we have the GPU as the host. So the host, with the host we mean the CPU, that is the powerful machine, yeah, that has control over the operating system, I/O, and so on. And then we have the device, which is which is the GPU, where these things are executed. And on this device, there are so-called kernels that are called from the host, together with some information of a number of threads that are supposed to be operated and so execute n threads, and they are then executed in parallel or sequentialized. So but you always think about them, everything runs in parallel. Okay, so there are, and the way this is organized is there are blocks, and every block has a number of threads. Okay. Now, example, how does this work? We have to define a function that runs on the GPU. The way we do this in the Cuda programming language, so Cuda is basically C, yeah, but with these extensions. So what we do in Cuda, we have this keyword ___ global ___, that indicates that this is the definition of a Cuda kernel that runs on the GPU. So this is here declared as a void function and then as an add, and then it usually gets vectors to data. Okay, you need to know that each thread is called with the same arguments. Yeah? So it's usually not possible to pass your data by value. Also, it is the amount of the number of arguments here is very limited. I think I don't remember how many, but so it's doable, but you easily get into the problem if you have to pass a lot of data. You have to build a struct from which you extract this. Yeah, so because it's very limited, the number of elements that you can set here is very limited. So as is with MPI is when that everything is called with the same function, and so that not everybody does the same thing. The first thing that the Cuda global function has to do is to identify which thread it actually is. Yeah, and this is okay. We'll come to a little bit more details how this is done in practice, but they have the thing is they know their block ID and they know their thread ID, and from these two informations, what you have to do is you have to say you as the programmer has to think up a method to identify who you are, because block ID plus thread ID together they are unique. Yeah. So, for example, here I'm just using block ID for whatever reason. And then I do here okay, I'm summing up these things. So now what is important to know how all of this works. Since we are not Apple M1, which has a shared memory between GPU and CPU, we actually have different memory for CPU and GPU. Yeah, so your GPU usually in the laptop it may be different, but usually it has its own memory, and for performance this is also extremely important because, as I said before, on a modern GPU the memory is physically attached right to the GPU. Yeah. To have as small a distance as possible, because these things are so powerful that almost all the time that you need to wait is just by getting into the memory. Now, therefore, it would be very difficult. I mean, it would be very inefficient if the GPU has to access the memory of the main on the main board, which is physically possible, but being very inefficient. So this means there's different memories in your main computer and in the GPU, and what you have to do in order to actually get your result out is you have to copy the memory from the GPU memory onto your onto the CPU memory. So what you usually start with, because you have your data on the host, yeah, is you have to call, before you do any work, you have to call Cuda memory copy. And here, the first entrance, the first argument of this function is always the destination. So in this case, when you do a copy from the main memory to the device memory, then you place here the address in the device memory. Yeah? So this is the pointer to the device memory, device A. Then you are okay, so you're copying, so this is the destination, and this is the source. Yeah, your source is this vector on the host. Then this data has a certain size that you have to copy, so it's n times, you'll say n integers, n size of integer. Yeah, that you have to copy, and you have to tell them the direction from host to device. Yeah, and always remember, yeah, also for the exam, destination and source. I find this annoying because in English we say from to. Yeah, and here we say to from. Okay, please remember this. So, and then here you call this, and the way I set this up, which is potentially not very clever, is I'm only distinguishing by their blocks. So I'm only using one thread in each block, which I believe is a very stupid. I should do it the other way around. I should use n threads in a block, but now I'm using n blocks with one thread each. So depending on what you write here, it may be more or less inefficient, yeah, more efficient or less efficient. So, in addition, when you call this function add, that is executed on the device, on the data that has been copied to the device, yeah. So they can only use pointers. They can only use pointers on the device, not pointers, because this is an address. You have to know in which country you are, right? Before you give an address. Yeah. In addition to its usual arguments, you also need to give him the arguments on how many blocks do you run and on how many threads does one block have. And these arguments are given here with this triple chevron. Yeah, it's put in this triple chevron way here. So, okay, you call them, work is done here, and then if you want to know your result, you have to copy it back. Yeah, and now remember, destination source. Yeah, so this is, you copy it back to the host from the device. You have to give the size what you copy, and then memcopy device to host. Okay. Anything unclear? I never know whether you are listening. maybe you already know all of this. I don't know. How familiar are you with Cuda already? You are familiar. Yeah. Okay, so there's a very basic entry today, yeah, but then you can give a little bit of exercise later. Right. In addition to this copying, we also need to allocate the memory, of course. And last time we talked about the old-fashioned C style to allocate memory, because nowadays I think people learning C++, I mean, already for 20 years, I would say they never need to deal with allocate, yeah. So you could always use new, yeah, to allocate, to let the operating system allocate your memory, new blah blah, and then you call the destructor, yeah. So in that sense, Cuda is is actually C style and not C++ style. So you have to do an explicit allocation in the old-fashioned way. And here is a reminder how you do this in C++. In the old-fashioned C style. Yeah. So you have a pointer to the memory on the heap. Yeah. So you first have to declare these pointers. Then you do a memory allocation, malloc, of a certain size of memory. Yeah? So you get the entries, and then you say, then the size of operator gives you the number of bytes inside for that this machine uses for storing this type of this data type. Yeah. And remember, this is not fixed design. So there's different machines store floats with different number of bytes. Yeah, so you cannot just assume something. So this is how you get memory allocated on the host, and now in Cuda you do it in a very similar way. So you need pointers, which are now pointers on the device. Always remember, this is an address, and for the address you also need to know in which country you are before you call it, because this is the same address on the host gives you something else, obviously, right? So here we have the function Cuda malloc. It works a little bit more modern. Yeah, so this has no return value. Instead, you pass the pointer by reference, and still you give the size of your data. So, I mean, one thing that you have to remember here, usually you have to store things twice. You have to have a copy of your data on the host and a copy of the data in the device. Otherwise, there's no way of accessing this. So, I mean, in principle, you can go download a single value from the device, yeah, but that's kind of complicated and expensive. So yes, so what we already had before is this copying. Now I'm repeating myself. We always start here with the destination, then comes the source. We always have to specify how much we copy, and we have to give the direction, Cuda mem copy host to device or mem copy device to host. And this goes through the PCI Express bus. Okay, any questions? No. Freeing memory. So everything you allocate, you have to free. And in C style, this works like this. We get free to giving the pointer, and then it will remove from the heap this amount of memory that you had allocated here. And freeing memory from the device works in a similar way, which is called Cuda free. And please remember, not freeing your memory does not cause you pain immediately. It causes you pain later. Therefore, be careful. So, then there are basically three types of Cuda functions, of which we discuss here too. Namely the kernel and the device function. So the kernel functions are the functions that you call with many different threads, and they are called from the host in your host program, yeah, in your host C program, and these functions are indicated with global. So they are executed for many threads. Then on top of this, there are the device functions. And the device functions are usual functions that usually give you a return value, for example, yeah, and they are called from within a thread and within a thread on the device. So there is a possibility to declare a function also as host device. When you declare a function as host device, then the compiler will compile it twice, once for the device and once for the host, so that you can call it from the host and you can call it from the device. So a device function can only be called from the device, meaning it can only be called from within a global function. So, and how is the global function being called? So the kernel function are called with the number of blocks and the number of threads within a block. Yeah, for example, the add function that we had here is add, which we call with 1 blocks, and within 1 block we allow 256 threads. Now, obviously, it would be more convenient if we did not need to think about this number of blocks or threads and just say, okay, I will so and so many threads. Yeah, but there is a hardware organization of this, and this may cause your program to be executed quickly or slowly, right? And so for example, I may want to say that I don't care about blocks. I just want to have many threads. Yeah? But there is a hardware limitation to how much threads I can have in a particular direction of my block. So here, so why do I say direction of a block? Because this is one-dimensional, but you can also give three-dimensional. We come to this in a minute, blocks and threads. So blocks, we can have apparently we can have many blocks, but not so many in each different direction, but only 56,000 blocks in each direction x, y, z, and we can have only 1024 threads in each block in the x, y direction, and in z direction. Remember, we come from, this is for graphics cards, so usually we are dealing with two-dimensional stuff somehow. Yeah, there's only 64 in the z direction. So now, you see, this is much less than we have processors on the graphics card, usually. So you often have loops that would go over more than 1024 objects. So you cannot just use threads. You have to organize your data in a way that it actually covers your entire problem. Yeah, so you have to use blocks and threads. Yeah, and also remember the way you arrange it may also have impact on your performance. Now you need to locate. Okay, how to locate your threads inside your block. For this, each thread has 6 pieces of information that it can use. So we get the block ID, and we get, it's 9 altogether, yeah? We have a block ID, and we have a block dimension, and we have a thread ID within the block. Because these blocks are intrinsically 3-dimensional, they have an X, a Y, and a Z component, even if you call them just with one number. So if you just call them with one number, as we had in the previous, or actually down here, yeah, 8 and 2, they will assume that this will go to the X direction of the block and the thread. So basically, the block dimension, a block dim Y of this call here would be 0, yeah, because we don't have any block in any data in Y direction here. But it's your turn to arrange your data in such a form that you can extract the information from the thread like this. And what is usually done to get a unique number here is to use a block ID X times the block dimension. So, for example, if in this here this is 8, so the block dimension is 8, meaning there's 8. Okay, let me block dim, sorry, no. Okay, I got it the wrong way around. So this is 8 blocks. It's 8 blocks, and each of them have a dimension of 2. Yeah? Maybe I should do it the other way, 2 blocks with 8 each. That may be more efficient, but this for the purpose of understanding what we are trying to do here. So now we have block 0, 1, 2, 3, 4, 5, 6, 7, yeah, and each of them has has just 2 threads each, yeah. Okay, so this ridiculously small example here is not useful in practice. It's just for understanding this method here. So we'll have to find our entrance here. Hopefully I made this correctly. So we'll have, say, we are in block. Okay, say this is block 5. Okay, this is block 5, thread 0, right? So this is because the block size is 2. So we are in location 10 on the array. So now we identify our data that we want to process in this way, and see we are here, we are this thread. Okay. Clear? Yes, so we can do this with multiple dimensions. So there's a data type for this. Yeah, this is dim3, yeah, where it's just a vector with 3 entries, if you will. Yeah, so can build a grid 16, 16, 16, or block 8, 8, 8. So this now gives you this is the name that we specify, yeah, for this, and then we can hand this to our function, and then this function has the ability to distinguish between x and y and y separately. So you don't need to do any complicated computation to get something out of a one-dimensional array, because your way of addressing has already 3 dimensions. Yeah? So you can imagine this is useful for dealing with graphics objects. Yeah? So that you can actually give the coordinates, identify the coordinates of your pixel that you want to operate on. Okay, calling device function, no, there's nothing strange here. It's just your, for example, get device function as a float, say square, yeah. So this function can now be called from within a global function. A global function cannot call a function on the CPU, obviously. Yeah, that wouldn't make any sense. Yeah. So we can call this from within from within the global function. For example, here, so ai equals to square ai, yeah, and then this function is being called. Seeing this example here is for demonstration. Try not to call too many device functions. This may cause, calling device functions can lead to sequentialization. Yeah, so and maybe very expensive. So sequentialization is, we'll have this in a minute, maybe on the next slide. Yes, we already. So sequentialization means that things that you would like to have done in parallel will be done sequentially, because there is hardware reasons for this, or physical reasons. So the GPU is a SIMD machine. It can execute sets of threads in parallel, but not infinitely many. The things that are really done in parallel, so where at the same clock cycle you do exactly the same work, just on different data, on Cuda is called warp. Yeah? So like this is warping through your data. In Cuda, the warp size, as long as they haven't changed it for their new machines, is apparently 32. So they always do operations, 32 operations at the same time, but they need to be exactly the same operations. They have to be executed together. So this also means if you have less than 32, you don't save anything. Yeah? This is the minimal size how it actually can execute anything. So this leads us, again, as we had last time already, to the question, what is if within one warp you have branching? Because branching in Cuda is allowed, and it's not difficult to implement. You just have an if-else statement, for example. Yeah? So if you have branching, what happens to your warp? And the thing is the same as we have discussed it last time. If you have branching always leads to sequentialization, which can be acceptable in cost and can be very detrimental in cost. Anyway, so what happens if, for example, you have your kernel function like this, that you have a single exception, which we kind of often have. So there's an edge case. Yeah? So there's an edge case where you want to do something else. So if we are at the end of the block, we want to do one thing, and for all the others, we want to do something else. So what the machine then does is it sequentializes this warp, because what it can do is it can put any thread inside the warp to mute. Yeah? So not doing anything. So it will now execute this one thread here, and all the others are muted, while then it goes to the next branch, and there it executes all the others. So obviously, this can give you some headaches if you put a lot of branchings inside of each other, then your program becomes very, very inefficient. So for example, what you could consider doing here instead of branching here, if it's really an edge case, you may want to do this on this edge case on the CPU after you downloaded your data. Yeah, that may be much more efficient than to include your edge case into a global function. So we are already coming to the end of this here. There's one more thing, okay, two more things that I want to talk about. This dealing with device memory and host memory separately is kind of inconvenient to the programmer. Therefore, what they introduced from Cuda release 6, and I told you that I'm an old guy, and we are using we started kind of with Cuda 1, so we have actually devices running that do not support this, even though this is now supported for the last, I don't know, 10 years or so. So we are usually not doing this for multiple reasons, but what you can do is you can allocate the memory of the device and the host, I would say, together. From your programming perspective, this looks like there was only one array that you have to use. Because you also address this by having only one pointer, interestingly. Yeah? So you declare one pointer that is valid for both the device and the host, and you use Cuda malloc managed, and this, what it will physically do is it allocates memory on the device and on the host, and if you write on this from the device, it will write on the device version of this, and if you write on this on the host, it will do it on the host. And managed means there is some magic behind the scene. So this makes C programmers very, very nervous. Yeah, it's like scripts, like script programming here. So there is some magic behind the scene that when you modify data on the host and you want to access it on the device, it does automatically the copying for you. Why? Okay, tell me that I'm losing my voice after talking for 4 hours now. Tell me why this makes C programmers nervous. I mean, it's convenient. And C programmers are not convenient, yeah, but they don't care about convenience. The C programmer is used to know what the machine does. Yeah? I want to know what the machine does. If you are a Python programmer, you don't care what the machine does. You only want to know, you only want to see your results. So problem here is you don't really know what the machine does. So you can do something that looks pretty innocent. Yeah, you have a very innocent operation. Like, I mean, you can do the same thing. So you're just looking up a value in your matrix. Yeah, and if the last time you changed your matrix was on the host, and you're reading from the host, then this will not cost anything. But if you do exactly the same thing, and the matrix has recently been changed on the device, this means that the matrix is copied from the device to the host before you can read any value. Even if the value that you read was not modified. Yeah? So you're no longer under control. The machine takes the control. Very convenient, dangerous. Okay? So, because physically, this is important, physically you have two copies. But you see, this gives you a more convenient way of, gives you a shorter program, for example. Now look at this. Suppose we have this global function here, which would be the same thing anyway, and then how would we deal with this without what is this unified shared memory? Yeah. I mean, okay, go back to the word. The name annoys me because it's not shared memory. Shared memory is when you really share memory. This memory is not shared. It's, it has a copy. Yeah. So it looks like it's emulated shared memory. But this is a marketing term. Yeah. Okay. So what you do when you don't have unified shared memory? So you need to have pointers to your data on the host and on the device. You have to allocate the memory on the device, and you have to allocate the same amount of memory on your host. Then suppose, I mean, they can be different, but suppose you initialize your data on the host. Yeah? Then after doing this, you would have to copy this memory to your host, and then you do the calculation, and then you do something else. The doing something else usually means you copy the data down to the host again, because usually you do computation because you want to do something with your data. By the way, that's a problem. You know why this is a problem for graphic cards? I mean, graphics cards are not designed to return values. They are designed to throw data on the screen. I mean, this was for a long time, this was the biggest problem, is to getting the data out, because everything goes to this very slow bus. Yeah. So now, I mean, first, okay. So you have to copy stuff down, which the graphics cards originally is not built for. Yeah? And then you can access this, and then you have to free everything. So instead, if you have unified shared memory, what you do is you allocate things as managed, where you use only one pointer to an array. Then you initialize the thing on the CPU, and then you immediately call this function without notice. So there's no notice that when you call this function, everything must be copied. Yeah? And then you do something else, and then you have only to call free once. So by freeing this, you'll free the memory on both sides. Yeah? I mean, one other consequence of shared memory would be that you would assume you would have twice the amount of memory that you could use. Yeah? You have to remember you have 2 copies of this, so this takes up also space. Yeah. Yeah. So, okay. Now this brings us to the end, actually, of this lecture, and to a little bit the discussion how we would going on to write this. So we need some infrastructure, yeah? So we require as an include the Cuda runtime, yeah? Inside the main function, what we could also do, which we are not going to do here, or we could do it, but I usually don't do it. We can set a Cuda device, yeah. So so if you don't set a Cuda device, it will run on device 0. Assuming that you have only one graphics card in your computer, then this will be device 0. In the machines that the boys have up there, they have, of course, several graphics cards so that they can also run things in parallel. So you can also, I mean, of course, you can also combine Cuda with MPI, yeah, exchanging data between devices. Then, now I can happily announce that this here we cannot run on the input nodes, on the login nodes, obviously, because the login nodes don't have GPUs. So in Phoenix, this job file has to include as a partition that it has to run on a GPU queue. And the last thing that we need to know is that, of course, we have to compile this with a Cuda compiler instead of a C compiler. And this Cuda compiler is from NVIDIA. This is why it's called NVCC, so it's a C compiler. Yeah? So it's not a C++ compiler, but a C compiler, and the Cuda program is usually named as .q, and otherwise it works like in C, usual C compiler. So yesterday the cluster was dead. Yeah. So I don't know whether you noticed. So no time for me to prepare anything particular. But let's have before we go to doing some exercise. Let me see whether I'm in the right. Okay, yes, I'm in PVR 2025, and there I'm in my folder and in Laplace 2D, and here, so this is your homework, right? Where you are supposed to implement this diffusion kernel with MPI. There is a job file Cuda, which actually we have newly done here. So important is, okay, it's using GPU Q2, so there are different, I think there's 1, 2, and 3. I don't know why we have here 2, I don't know. And this is supposed to call the Laplace 2D Cuda. So the Laplace 2D Cuda, I've run this several times here. Yeah, so this is what you have to call to actually run this. It's supposed, the CMake file thing has already compiled this into bin, I guess. Into bin, right, here it is. Yeah? So the source is Where's my source? Testing, wait. No, it's not bin source, it's, sorry, here. I don't know why there is a source in bin. Maybe just for the, okay, so there is, forget about build for this for a moment. So we have, in Laplace 2D, we have source, and in this here we have the Cuda version of all of this, okay? Now, I hope you have made yourself familiar with this already. Okay, so the way this works here, there is includes Cuda runtime.h, and the thing I was not aware of is that there is a Cuda helper.h. Okay, apparently I have to, yeah, okay, so the Cuda helper.h is okay, so the Cuda helper.h does something like setting up the device and leaving if there is no device found. Yeah, okay. I think we'll leave it at that and look actually back to our Cuda version. So when we use Cuda, we have to put everything, so we actually have to put the execution here into a function. Yeah, this is this global void calculate time step, so it gets the pointers to the data, and remember this is always the entire data. Also the mapper, yeah, and then once we are inside the function, the first thing we have to do is to use the block ID, the block index, and the block dimension times the block index plus the thread ID to identify which thread we are and what we need to execute. Yeah. So from this, now we get our x and y coordinates. Yeah, we get our data. We do, and then So this is basically this finite difference function that we have to execute here. Now what you see here is there's no loop. Yeah. So this is called for the entire matrix. So the entire matrix, every point in the matrix has its own thread. So, and then what we do here is int device. So we set the device to 0. I believe this is not necessary because it would use device 0 as a default. Then there is the usual stuff that we had before. We have inner. Okay, so the inner grid. So now what is done here is kind of the modern way of doing it, if you will, or the managed way of doing it. We use only one pointer on the device and the host for the old data and the new data, and we allocate the memory in a managed format. Yeah. And then there is some error checking that I don't want to go into any detail. So the rest here is mostly the same as before, and the only thing is when we come into the iterative loop. Yeah? So we call the iteration from outside and call these functions with now our, okay, we have a block size of 256, and in order to get the num blocks, block size. Okay, block size is the number of threads, basically, yeah? Block size is the number of threads, and then given the amount of data that we have, so the entries in our matrix, yeah, we now have to compute how many blocks do we have. So this is then the size of the inner grid that we want to process divided by the block size, right? This is the number of blocks that we have, such that number of blocks times block size is again all the points that we want to process. And then we do the iteration outside, from the outside. And there's one thing that again old guy has to remember and telling you. One problem with Cuda. So please remember, graphics cards are there for displaying graphics. Yeah. One challenge here is that the operating system does not wait for a Cuda call, for a call to the graphics card, which is actually kind of a problem. So if the graphic card does not return, the operating system assumes the graphic card somehow has crashed, or the program has crashed, and it will overwrite this. So there is no clear rule, and maybe now more people are using GPUs for other problems. This will be for other things than doing graphics. This may become less restrictive than it was in the past, but the thing is, the operating system can cancel your Cuda call at any time it likes. So the way you survive is that your Cuda call cannot run for a very long time. Yeah, so you do something, then you quickly return and you give another call. Yeah, so this is, you see, this is the reason. Well, we don't loop over the points, but we loop over the steps. Yeah, because we depend on the function returning quickly. Yeah, the graphics card done with its job quickly, and then we call it again, because the operating system depends. You have no control. Windows, Mac, Linux, they will have different times that they think appropriate for calling a Cuda function. Yeah. So the iteration is done outside, and you call the function again and again and again. Okay. So there's an error check that again I'll skip over. Then here, because we have the data managed, we can do the swap, which I doubt that this is okay. Now, okay. So this is a good question. Does this swapping include a copy? No, I don't think that the swapping includes a copy, because it's just exchanging the pointers. Yeah, so it would not need to copy the data. Yeah, so that should be safe. And then, okay, done with our work, and we call Cuda free. I have run this thing previously. I guess I'll just so this was the last should have been the last one that I, funny enough, didn't I? This was the wrong one, how? Okay, so I think yeah, here. So okay, let's just do this again. Yeah, I'm already in the Laplace 2D. Folder, and I call sbatch job file Cuda. So now the job was submitted as 101,597. So let's see whether it has returned. Apparently it has returned. So this is this one. Let's open this. Unknown error. Okay, that's interesting because when I called this previously, before the lecture, I got this result. Yeah, here we get 24,000 node updates per second, which I believe is better than what we get with all the other methods. And I have no idea why now this didn't work. Very annoying. Environment variables, load modules, lim have inconsistent lengths. Okay, I have one thing up my sleeve that I could try, because sometimes it only works. I don't have an idea why this is, but module load. I mean, really, I run this before we took this lecture. Okay, I put in this here, so I'll include module load Cuda 11.3 that it uses telling that it's using the runtime of Cuda 11.3, and then I'll try to run it again. So then I'm not in the wrong folder because it gets the output right here, right? So I must be in the right place. Let me see whether, okay, we get an output. And we get our crash again. So annoying. Okay. Okay. Anyway, we saw the result that we had before the lecture. Actually, we'll now have a break and then come to a little bit exercise. Thank you for listening.